Welcome to Gradient Daily, where we dive deep into the most significant AI research papers. And today, we are digging into a seriously groundbreaking paper from Meta's superintelligence labs called SAM3D, 3D-ifying anything in images. Now, this isn't just a small step forward. This work completely flips the script on how we teach machines to see our three-dimensional world, using nothing more than a single, flat 2D picture.
So let's just start with the magic trick, because that's honestly what it feels like. You take a normal photo, right, like these ones here, and a SAM3D just goes in, pulls out every single object, and reconstructs them as full-on 3D models you can actually interact with. It gets the shape, the texture, and even where everything is supposed to go in the scene. I mean, this is one of the holy grails of computer vision, and what we're seeing here is just a massive leap towards making it a reality.
But, to pull off a trick like that, the researchers had to break through a problem that has been a total brick wall for 3D AI for years. It's a fundamental challenge that's held back progress for a very long time, and it's called the 3D data barrier.
All right, so here's the game plan for today. We'll start with why single-image 3D is so tough. Then we're going to unpack SAM3D's really clever training strategy, which is inspired by large language models, and we'll look at its secret weapon, this human-in-the-loop data engine. After that, we'll pop the hood on the architecture, check out the incredible results, and then wrap up with where this all goes from here.
Okay, first up, the single-image 3D challenge. Let's really get our heads around the core problem here. How in the world do you teach a computer to figure out a complex 3D scene when all that has to work with is one flat photo? It's a fundamentally ambiguous problem.
For us humans, this is a piece of cake, right? We do it automatically. Our brains are just wired to use all these little hints that psychologists call pictorial cues. Stuff like shadows, perspective, textures. We see a car from one side, and we just know it has a front, a back, and four wheels. But teaching a machine that kind of intuition, well, that's a whole different ballgame.
So, you might be thinking, okay, why not just do what we always do? Let's just train a massive model on a ton of data and call it a day. What's the one big thing that's stopping us?
And the answer really comes down to one thing: training data. Or more accurately, a huge, massive lack of it. Just think about what you'd actually need. You'd need millions, maybe billions, of real photos, and for every single object in every photo, you'd need a perfect 3D model to go with it. I mean, it's just impossible. A skilled 3D artist could spend days on one model. There's just no way to scale that. And that, right there, is the 3D data barrier.
So how did the SAM3D team get past this giant wall? Well, they realized they needed a totally new approach to training, and they found inspiration in a pretty interesting place. They basically borrowed the playbook from large language models like GPT.
This image right here is awesome because it lays out their entire strategy. This isn't just one big training run. No, it's a super carefully planned pipeline. It starts the model off with super clean synthetic data, and then it slowly, step by step, introduces it to more complicated, messy, real-world stuff, making sure it aligns with what we humans expect to see. We can break this whole process down into three main phases, and each one has a really specific job. You've got pre-training, then mid-training, and finally post-training, which is all about getting it ready for the real world.
All right, step one, pre-training. Think of this as 3D kindergarten for the AI. It's basically force-fed millions of clean, perfect 3D models of objects in isolation, shown from every angle. This is where it learns the basic grammar of 3D shapes, like what makes a chair, or what a ball looks like from the top versus the side. They used a massive synthetic data set for this.
Then comes mid-training. This is where the model kind of graduates and starts to see how messy the real world is. The researchers did something really clever. They took all those clean 3D models and digitally pasted them into real photos. This forces the model to learn really important skills, like figuring out the shape of an object when something else is in front of it, and understanding where things should plausibly go in a room.
And they used two really smart tricks to make this mid-training data. First, something they call flying occlusions, which is basically digital chaos. They just throw pairs of objects into images to teach the model how to handle things being blocked from view. And second, object swap, where they find an object in a real photo, cut it out, and drop in a synthetic 3D model of a similar thing. This teaches the model all about context and realistic placement.
And finally, we get to post-training. This is the last step, the final polish. After all the synthetic stuff, there's still a bit of a gap between the training world and the real world. So this stage uses real-world data, collected in a super ingenious way,
to fine-tune the model and make sure its outputs look good and accurate to us humans.
Now, this post-training stage, this is where the real genius of this paper is. It's all powered by something they call a model-in-a-loop data engine. And this isn't just a data set, it's a living, breathing data creation machine. And it's the secret weapon that finally breaks that 3D data barrier.
The whole thing is built on one simple but incredibly powerful idea. Like we said, you can't ask a random person to create a 3D model from scratch. That's impossible. But, and this is the key, you can ask that same person to look at, say, 8 different 3D models and just pick the one that looks the most like the object in the photo. Humans are great at that. It turns an impossible creation task into a super easy selection task.
So here's how they built a pipeline around that idea. It's a multi-stage process. First, a human annotator just draws a box around an object in a picture. Then the system, which includes the SAM3D model itself, generates a bunch of possible 3D shapes. All the human has to do is look at the lineup and pick the best one. Then they just make a few final tweaks to the position and scale, and boom, they're done.
And this is what creates this amazing feedback loop, what they call the flywheel effect. The model helps make the data, the humans pick the best data, that better data is then used to train a better model. And what does a better model do? It generates even better suggestions the next time around, which helps the humans create even better data. It's this incredible self-improving cycle where the model literally helps itself get smarter.
Now, this whole idea of a data flywheel sounds amazing on paper, right? But this is science. We need to see the proof. Did this whole complicated process actually make the model better over time?
Oh yeah, it works. Big time. This chart is probably one of the most important ones in the whole paper. It tracks the model's skill using an ELO rating, kind of like they use for chess players. Each bar is a new version of the model after another spin of that data flywheel. And as you can see, the quality just climbs up and up, consistently and significantly, with every single iteration. This is the proof that the engine is real.
And the scale of this whole operation is just wild. Because they made 3D annotation so much easier, they were able to process nearly 1 million images. This ended up creating a dataset with over 3 million 3D models matched to real-world pictures. For this kind of task, a dataset that big was just a pipe dream until now.
Okay, so we've covered the why, the revolutionary training philosophy and the data engine. Now let's look at the what, the actual SAM3D model they built to run on all this amazing data.
At a high level, the model itself is split into 2 main parts that work one after the other. It's a smart design that breaks a really complex problem down into 2 more manageable steps. First, get the basic shape and position right, and then worry about the details.
Think of it like a sculptor and a painter working together. The first stage is the geometry model. It's the sculptor. It's a big 1.2 billion parameter model that looks at the image and carves out the rough, basic 3D shape and figures out where it sits in the scene. Then stage 2 is the texture and refinement model. It's the painter. It takes that rough sculpture and adds all the fine details and color, making it look realistic. Here's the full blueprint. Let's look at the top half first. That's the geometry model. It uses a really cool design called a mixture of transformers. Basically, it has separate processors for figuring out the shape and figuring out the layout, but they can talk to each other. This is super important because an object's shape and its position are obviously deeply connected. Okay, so once that first stage spits out its rough 3D shape, you can think of it like a low-res 3D pixel grid. That gets passed down to the bottom half, the texture and refinement model. This part uses a different kind of transformer to add all the high-resolution details and paint on the texture, giving us that final, beautiful 3D object.
All right, so we've got the clever training, the incredible data engine, and the powerful architecture. It all sounds great. But now for the million-dollar question. How well does it actually perform? Let's check out the results.
The results are, well, it's a knockout. It's not even a close fight. They had humans compare SAM3D's outputs against other top models, and as you can see from these charts, people preferred SAM3D by a huge margin, like over 5-to-1 in some cases. In AI research, a gap that big isn't just a win, it's total domination.
And when you look at these side-by-side examples, you can see why with your own eyes. On the left is the input photo, in the middle is what SAM3D creates, and on the right are the competitors. Just look at how much more coherent and accurate the SAM3D scenes are. The shapes are better, the layouts are more believable, especially in these really cluttered, tough real-world photos. And the hard numbers tell the exact same story. This table might look a little technical, but the story it tells is crystal clear. On all the important metrics for geometric accuracy, SAM3D is just in a different league. The numbers are dramatically better than all the previous work. This isn't a small improvement, it's a huge step change for the entire field.
And this chart right here is the proof in the pudding for their training strategy. It shows how much the model's error goes down after each phase. You start with just pre-training, then you add mid-training, and boom, the error drops. Then you add the final post-training with the real-world data, and the error gets cut in half again. It's just clear, undeniable proof that every single step in their playbook was absolutely crucial.
But hey, no model is perfect, right? So let's take a balanced look here. Let's talk about the incredible strengths of SAM3D, but also its current limitations and what this all means for the future.
So on the plus side, the list is long. Its performance on real-world photos is the best we've ever seen, period. The training strategy itself is a huge contribution, and the way it handles shape, texture, and layout all at once is a big deal. On the flip side, it's still limited by a basic fact. You can't know what the back of a chair looks like if you can only see the front. So it can get confused by really weird objects or angles. And of course, it's only as good as the data its own engine produces.
This paper just blows the doors wide open for future research, and it leaves us with some super exciting questions. Can they make that data engine even more automatic? Could they use this same approach for video to reconstruct moving scenes? And the really big one, what happens if we just scale this whole thing up? 10x more data, 10x bigger model. What new abilities might pop out?
Phew. Okay, we've covered a ton of ground, so let's boil it all down. If you're going to remember just a few things from this deep dive on SAM3, what should they be?
First, the training playbook is the real hero here. The way they train the model is the core innovation. Second, that model-in-the-loop data engine is a game changer. It creates a virtuous cycle that basically solves the data problem by making the model part of the solution. And third, what this all adds up to is a massive leap forward for 3D perception, one that could unlock all kinds of new applications in robotics, AR, VR, and a whole lot more.
So I'll just leave you with this to chew on. We're getting really close to a future where the line between a flat photo and a 3D world just disappears. If any picture you take can instantly become an interactive 3D space, how is that going to change everything? How will it change the way we create, the way we play, and the way we interact with our digital world?
All right, that's our deep dive for today. If you found this valuable and learned something new, we'd really appreciate it if you'd like this video and subscribe to Gradient Daily. We'll be back tomorrow with another breakdown of the latest in AI. Thanks for watching.